Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're gonna talk about atomic clocks on PCI cards. So let's dive deep into it. So many people have already covered this topic, so I want to cover why exactly we are bothering with this. Well, so first is problem. What exactly is the problem? Well, our computers are fast, like they are freakishly really fast. So we are kind of numb to it, but I would like to give some context. So whenever you say 4 gigahertz, oh, my computer only has 4 gigahertz of base clock, I'm so poor that I only afford 4 gigahertz of like base clock. What does that mean? That 4 gigahertz mean? Here's the 4, cool, 0, 0, 0, 0, 0, 0, 0, 0, 0 cycles in a second. That's how many times it's going per second. Now that number is so huge that nanosecond is fat for its calculation, meaning if you try to use nanoseconds, you have to use either fractional or decimal, like 0.25 nanoseconds. So let that sink in. This is beyond stupidly fast. Like our current computers, they're crunching data like there is no tomorrow, and like they're crunching inside a second. So it's super duper fast. And if you really want to understand how modern computer processors are working, you need picoseconds. Nanosecond does not have enough resolution. You need picoseconds to figure things out and to properly measure it. Oh, this clock is working, this clock is lagging. Or if you want to that level of resolution, you have to jump to picosecond. Now here's the ironic part. You can have the same motherboard that has this GG amounts of 4 gigahertz system, or maybe even 5 gigahertz, and the clock, the real-time clock it has, most likely, again, not necessarily not in our model, but most likely it will be 32.768 kilohertz crystal oscillator for your clocks. Let that sink in. Gigahertz, kilohertz, and you may find better basically oscillators generally around networking area. So you may find things like this where you could have 12 megahertz or 30 megahertz, 26 megahertz. 26 megahertz is kind of common, but you will find something like this in around your network area for clock syncing. And you will like, wait a minute, there are still multiple zeros below. That's the whole point. Our time is the weak link at this point. So you will hear these 4 digits explained multiple times. So I'll try to give some context. 1 second, you stretch that puppy to 1000 times, that becomes a millisecond. Take a millisecond, stretch it to 1000 times, that becomes a microsecond. Take 1 microsecond, stretch it to 1000 times, you get nanosecond. Stretch nanosecond, 1 nanosecond to basically 1000, now you are at picosecond. So when people are talking about millisecond, that's this sort of level. When you're talking about microseconds, that's good. That's good. Like we generally, most of our day-to-day life, even Olympic events are generally at millisecond level. Microseconds are like where you are like, you're talking something serious. Nanoseconds, really freaking serious. Picoseconds, now you're talking about like world clock level synchronization. So this is the serious headache of us. Now, why is that a headache? Well, think of it this way. At this resolution, basically nanosecond resolution, which mind you is not fast enough. That's already too fast for gigahertz clocks. If you have a server which has multiple racks, each rack could be drifting from each other. And God help you if you have to do what we call distributed computing, meaning you are talking about a hypercluster that is spread around in like, let's say, kilometer kind of area. So one like a corner of the server literally will be ahead in time versus one that could be behind in time by few milliseconds on this level. And whenever you talk about internet, you've heard people using milliseconds. It has ping of this many millisecond. That's the millisecond. So if somebody says 400 milliseconds or 500 milliseconds becomes half of a second, this is the reason. So this is the huge headache. We are making amazing processor, no discussion about it. It's just that the moment we have to connect all of them, either over internet or in a data center or a database or a hypercluster, our bottleneck becomes the time. Basically, these puppies are just not good enough for syncing this amount of data. Like our processors are like, dude, give me data. I'm gonna do my job, but give me data. And we can't give it fast enough simply because time is the issue. Now, I'm saying time is the issue. So what exactly is the issue with time? Well, time does not flow at the same rate. Like no matter how accurate time clock you can build, no matter which atomic clock you can make a freaking mercury atomic clock, you can make cesium atomic clock, you can make hydrogen atomic clock, does not matter at all. You put a atomic clock of that caliber in Earth, it will work differently compared to you put one in Moon, it will work differently compared to you put one on Venus, it will work differently, put one on like Mars, it will work differently. Why? Time does not flow at the same rate. There is not universal time waterfall that is going from Big Bang to everywhere. It's not like there is a concentration, there is a dilution, there is high speed, there is low speed. It's not fixed. So fundamentally, it has flow to it, and that flow has to be calculated, and there are two core vectors that affect it. One is speed, another is gravity. And that's why I said, like, if you put atomic clock, it will be precisely working, it will be giving you precise second, but the second itself would be longer there, or faster. Yeah, it will be faster there. So you get the point, like time itself is not a fixed entity. This was the genius of Einstein, to realize that time is YOLO, basically. So that creates an issue, where it's like, how the heck you measure something that it itself is not fixed? On top of that, that's like atomic clock level issue. Then you have another issue, is that if you are not dealing with atomic clock issue level, or so to say, all your measuring instrument, especially with crystals, oscillators and all that jazz, they are affected by temperature, interference, magnetic field, electrical noise. All of these things are degrading the resolution. So on paper, you'll like, oh dude, this puppy should be accurate to few nanosecond. You run in real life, you'll be like, dude, I'm lucky if I get like 100 nanosecond accuracy. So that's the problem. Time itself is a floaty mess, because like you put a atomic clock on top of a place, it's completely different compared to atomic clock that is at sea level. And be mindful, what is a second? A second for humans is defined as a hyperfine transition between of cesium atom, basically 91926317770 hertz. Now here's the deal, the core principle of all atomic clocks is one. You have an element, all elements have this, be mindful, all elements have, we just for human reason decided that this is a second. That's it. It does not mean like like this has this property. Almost all atoms have. That's why I said there are mercury atomic clock, there are hydrogen atomic clocks, rubidium atomic clock. Almost all elements have this property where they're gonna resonate. Now what atomic clock does that is very precise about them is that they have a feedback loop, meaning you send a signal, they vibrate, they give off something unique. Basically you could have a gas cell that could be transparent at right frequency and become opaque at wrong frequency. There is a feedback loop. And you can have something in case of cesium, you can have like, hey, I'm firing cesium from A to B, and in the detector it will only hit the detector if the frequency is just right. If it's wrong, it will be attracted to other magnets or things of that nature. Like there is always a feedback loop. Now that feedback loop removes all other interference, because if you switch away from this frequency, if your hertz is just not right enough, you're gonna be deviated, and then you'll know. And using that feedback loop, you can calibrate it. It's self-calibrating tool. That's why we call atomic clocks such a high quality clocks. That's why you can put this in a satellite and still know that satellite is working. You just have to dealing with special relativity rather than, oh, my clock is broken. No, clock is working fine. You are dealing with the fact that time itself flows differently. And that's why atomic clocks are so high grade. They are not an oscillator that is affected by things. They are atom, generally very pure sample is used. And they're like, dude, I'm only gonna do this thing at this exact frequency. Exact. Like in case of cesium, this is the exact frequency. In case of rubidium, it's a different frequency. But you get the point. Like there is a feedback loop that ensures that you are just right. Now, what does this all mean? All it means is basically we have to track vigilantly, meaning there are people in almost every country that is working their ass off just to track time. So how do we balance all the time? Basically, how do we balance time on Mount Everest versus time at sea level? We don't. Basically, we take as much data as we can, create a gravity map as accurate as we can, and then we normalize it to a perfect sphere, and then create a universal time coordinate, and then we just like hope for it. So that's all we have. And we have to do this because time itself does not exist the way we think. Because again, as per the time flows at a different rate, and not to mention, this is just a number. So this frequency, we have classified it to be a second. So for this to hold any value, people have to track this puppy and track it over the centuries. We have to do this. So we have, thankfully, after we have entered the industrial revolution, we have starting to do that. And so far, we have not lost a single second. So for long-term accuracy and reliability, this has to be done. And then we come to another hassle. Once you really start to reach this level of precision, you reach a nanosecond level, there is a lot of noise. Now, where is this noise coming from? People walking around, moon going on top of your head, you are in a fighter jet, things, you are in a satellite. I suppose like at this level, space-time continuum is like basically at low resolution, space-time continuum looks like smooth. At high resolution, it's like it's completely bonkers. And this is a very good rendition. Like whenever we say like, space-time continuum is being bent because of gravity. So we generally show a two-dimensional thing, but real world is three-dimensional. So how the heck three-dimension is being done? This basically is like a gelatin that is being squished from a center point. Is something like that. So physics itself makes time hell of a hassle to deal with. So basically how your fiber goes to, like you could literally have two fiber connection. Basically generally all databases are linked in what we call ring network. Basically they never have one line, oh, A to B. They always have A to B, and then there will be like A to C, and then that C to D, D to again B. So they always have connection, fallbacks and all that. You could literally have exact same length, 300 kilometer, 300 kilometer. You may find different time. Literally photons will take different times. Why? Continuum, space-time continuum is like, nope, you know what, or it may be going from denser material, not joking, that will have an effect, and we have clocks that are precise enough to measure it. So this is the physics level problem. So how does this humanity deal with this? Well, we introduced GNSS, basically Global Navigation Satellite System. Now, when we are talking about satellite navigation system, we are thinking about is telling your position. Well, position is a side effect of time. If you know the position, you have to figure out how the heck you are calculating. You are calculating what we call trilateration, meaning you take 3 satellites minimum and you draw spheres out of them. How do you draw spheres out of them? You take the constant of light speed and then you calculate the time. That's why I said overall every satellite navigation system is just a super duper hyper fancy clock, which is very reliable. So that's how our humanity works reliably. Basically, the GNSS is basically beacon of hope in this chaotic world. That's how do your stock market work? Thanks the GNSS. How does your navigation work? Thanks the GNSS. How does electrical grid work? Thanks the GNSS. How does anything work? Thanks the GNSS. That's all there is to it. And to simplify it even further, specifically for aviation industry, UTC is used, basically Universal Time Coordinate or Coordinated Universal Time. I do not know which one is correct. So basically, it's a time zone that was designed very specifically to be free of time zone. So basically, this is time. So every other country is either plus or minus, but this is the time. Now, why is this? Well, this was designed so if you take off from, let's say, China and you want to land at, let's say, Sudan, you could literally have a scenario it's like, hey, I'm taking off at, let's say, 6 p.m. You may be landing at earlier than that. You could be like, hey, I took off at 6 p.m. I'm landing at 5 p.m. What the hell? To make sure that sort of calculation error does not happen, all aircrafts are internally working on UTC. The captain, when they say like this is the local time, they always have a clock on their dashboard that tells them what is the UTC. All the airlines works on UTC. Everything that is very critical generally has a UTC layer. So how do we deal with it? There is a layer on top of that, that is the offset. That offset is added to it and then we get the data. So how does your mobile know what is the time is? It knows the UTC and then it feeds in the data. Hey, I'm in India. Now, when UTC was created, countries wanted to, basically a lot of countries were trying to do what we call round number. Basically, you should be exactly either 1 hour ahead, 2 hour ahead, 3 hours ahead. Only few countries are there that are like half hour ahead, as in like India is 5 hours, 13 minutes ahead. World did not like it, but again, it's like our clocks have to sync to us. For that reason, we had to have this. And there are many other countries, you can list them down below, which has like that half hour increments. And be mindful, China is like very weird, where it's like, it's so huge, it's supposed to have 3 time zones, but they're like, no, 1 time zone. USA has like 4 time zones. So how the heck all this mess works? Because of GNSS. Now, how the heck GNSS can be that accurate? Well, here's the deal. First, there are multiple of them. There is GPS, American system, GLONASS, Russian system, Galileo, European system, Binju, that is Chinese system. And because all of these puppies are at core military service, money poured on them is like, there is no tomorrow. They're like, you want money, you get money. So all the atomic clock, they create a time. Where this time distributed? Because here's the deal. A standard does not mean anything. It's like, this is a centimeter. It's like, how do you know this is a centimeter if nobody else agrees with it? So you have to distribute it, right? So if you say this is a meter, you have to make an element and then give it to other ones and then they're gonna measure it. That's how it works. Like, transfer of standard as we call it. So how do we transfer the standards? Basically, these sort of super duper hyper accurate atomic clocks, basically in every nation, basically all these 4 nations, they work their ass off to have the most precise time, send their time to their satellite system, and that's how it's distributed around the world. So if you have a GPS receiver, you have super duper precise, basically you are getting direct reference data. And for time calculation, GNS data is classified as level 1. Like this is the level 1, level 0. That's like, this is the time. So if you are going below this, basically below the resolution that this puppy can provide, at that point you are at research level. So this is the modern backbone of our world at this point in time. Everything that works because there is some satellite navigation system that is providing the atomic clock data to everything else that needs it. be it stock market, be it your tele exchange, whatever have you. And there are multiple systems that also gives the redundancy, and there are also regional systems. For example, India has a regional system known as Navig, and there is Japan also has a regional service. I keep forgetting their name, but it's for there only. So what is this PCI card that is making such a headroom? It's like radiation in your card and like atomic clock in your card. So the idea is very simple. You take GNSS, which is the base of humanity's clock, and then you get it married to atomic clock. Now, like, why? Well, here's the GNSS. While it itself is awesome, GG, it does suffer from something known as atmosphere. You may not get the signal all the time. And again, overall, like let's say if your refresh rate is once basically 3 hertz, let's just say, you are refreshing 3 times a second, it's good enough for low level things. But if you want precise, you need to be refreshing at much higher rate. That requires a very clean weather. If your refresh rate goes, let's say 200 hertz, 500 hertz or megahertz level refresh rate, first you need military level clearance, and you really need very good weather, otherwise it will simply not work. So how do you make sure that you do not drift between this snapping? And not to mention, GPS while itself has never gone down as in like all the systems gone down continuously. So we generally have always 1 or 2 systems working without an issue, but there are times where it could be forced to not work. For example, if Air Force One is going above you, 40-kilometer area would be poofed off GPS. So in those sort of scenario, you may be like, what the hell now? Or sometimes interference could be there, other things could be there. Magnetic storms are also a thing. It could also wreak havoc on your basically ability to receive signal. So how do we solve it? Well, that's why you have to have atomic clock. So all these systems have a GPS receiver. This secondary card that you are seeing, those are the GPS receiver, and then GPS gives them the very precise time, and that time is synced with the atomic clock. Now, atomic clock on itself is very low drift. Now, these things are very precise, meaning they only drift by a nanosecond, not even a whole nanosecond in a day. Some are very good at that. They may be like picoseconds a day, but generally you cannot get cheap ones that are that good, but that's the whole point. They are fundamentally very robust. So all you have to do is like sync, let's say every hour. If you're syncing once an hour, your still would be damn precise. Now, has this been done? Yes. This is how your world works right now as we are speaking. This is exactly how this thing works. This is exactly the thing that you can find in basically YouTube servers and hyperclusters and basically anything. There is a giant server communicating, there would be this. But what's the problem then? Problem is, even though they exist, they were always proprietary and costly. How costly? Facebook could not afford them. CERN Collider could not afford all of them. Even military projects are like, yeah, that's difficult. Even supercomputers cannot affect too much. Like, can they buy it? Yes, 1 or 2 pieces. But imagine to really have high level processor, you may want every server rack to have one. At that point in time, the cost of those proprietary solutions, and not to mention, those proprietary solutions are proprietary to the nth degree, meaning you do not even know how the softwares are working. So if that software has a, let's say, a back hole, basically unpatched security vulnerability, lol, you have pushed your entirety of your server, which that's why many times people do not even want to install it. It's like they're gonna cost you arm and a leg and a kidney, and they're not going to tell you how it works. And most of them are 20 years old. They work. That's the solid thing. But it's not like, whoa. It's like, okay, good enough, but like you're charging an arm and a leg and a kidney for it. So people realized, Facebook engineers realized that we need something to change. If we really want to make hyperclusters and even more hypercluster, we need a way to transmit data from one end of hypercluster to another end of hypercluster precisely. If we do not do that, what do we do? If we do not have that, well, we just add latency. How much? 20 millisecond. In a multi-gigahertz computer, we literally have 20 milliseconds of latency. Let that sink in how much clock cycle we are wasting because of that. 20 milliseconds, your computers were like 20 milliseconds, it could be like, I don't know. So they built an open source system, and that was the easiest way to bypass all patents and all that. And they were like, okay, this is what we're gonna do. Everything in this is open sourse. The atomic clock, you choose whatever you are. That's why you have 3 one, like microchip one and Simtronics one, and there is this microsims one. Like there are many more also. And the FPGA units, this is like kind of fixed, standardized. And then the GPS unit, again, that also you can change based on your requirement. So they have built everything from scratch, and the idea is that you have a GPS receiver, you have FPGA that is doing hardware level corrections and all that, and then you have an atomic clock that is marrying all the data, and this is happening at hardware level at super low latency, and this is gonna cost you around $1,500. Like, wait a minute, This supposed to be cheap thing is $1,500. Yes, compared to the old, outdated, dilapidated proprietary BS, that's supposed to start at super cheap price of $10,000. From that point of view, if company is like, hey, I have hundreds of rack, if you ask them to add 10,000 rupee unit, $10,000 unit to every rack, that's painful versus $1,500. Well, that's like they can add multiple, and be mindful, 1,500 for you and I, if they're mass building it, the price will go down drastically. So from their point of view, it's chump change. And thankfully, because we humanity did learn from network timing protocol that while it was good, we were gonna need something better, and something better was built, and it is integrated in all your hardwares. It's called precision time protocol. It's pre-built, everything, router, your switches, your networking equipment, your computer, a network chip in your motherboard, network chip in your mobile phone, almost all of them have it. Consequences, it was never truly utilized because this never became a standard. Why? Proprietary and costly stuff. So hardware is there. Basically, you just slot in and you have a whole ecosystem. If you can put the software properly, you can just utilize it. And if you ever heard the saying that Facebook did this and magically they got 100 times more throughput, it's like, how the heck that's possible? If your hardware is the same, how the heck you got that? Because of the latency. They had to wait 20 milliseconds. So let's say one crunching of data, crunch, done. I'm going to send it out. But they're like, no, I cannot send it out. They will have to wait 20 milliseconds, send it out. Or attach a tag of 20 milliseconds and send it out. So that fundamentally created a lag point every time they are transferring data. Imagine that 20 millisecond goes down to, let's say, at good best case scenario, nanosecond. Or 10 nanosecond, 20 nanosecond. That would be like almost instantaneous data communication. That would be so fast, so elegant, that throughput would be exponential. And not the speed, let that be very clear. Speed would be exactly the same as it was, but the throughput would be like, whoa. And be mindful, even a proper basic level implementation where you're just turning on or turn on like basically PTP and like you're syncing and all that, they are able to bring down milliseconds to microseconds. That is more than 100 times better. So flat out response are like, whoa. You must have noticed that even if you have a very high speed internet connection, you may have many sites that are loading the frame of the site, but the content of the site, if it's specific to you, it takes time to load. It's like, dude, you loaded the frame. Why the heck these things? It's happening generally because there is a jumping points inside the network. It's not obvious in very high priority areas. Basically, governments, not government, as in like every private company does know, like, oh, this is the hot area, a lot of people are there, so they put high priority servers there. That does get good coverage. But if you are in odd area, you may find this very often, even with YouTube, where it's like the frame of YouTube loads instantaneously, but the material inside is like taking time. And that's happening generally because the file data is not jumping as quickly as it could jump. Not the network limitation, the timing limitation. So that's why this PCIe card is such a big deal. So what is going to be the effect of it? Well, a revolution. Flat out. You have to understand this core principle of everything basically is that you are only as fast as your slowest link. Meaning you can have a process that is like 10 gigahertz base clock. Awesome. Here's the deal. It cannot actually work at 10 gigahertz. It can, like, you literally have to load it in such a way that keep working for until you have like 20 millisecond slot left. So you have to understand, like, it's like, hey, I have this super amazing engine, super amazing horsepower and all that jazz, but the tires are like unable to actually work and grip. You're like, yeah, the tire is the limiting factor. So same thing happens here. Our computer infrastructure as of now is not limited by the compute power, not the crunching power. We got the crunching power. We just don't have the ability to sync at high speed with high throughput. So our fibers, our CPU, they need to be utilized. Basically, their wings are not coming out properly. So if we do that, then we will not be dealing with the sluggish world. That's why I specified. I can guarantee you most of you must have experiences like, dude, I upgraded the internet. And most of the time people say this, like, yeah, I upgraded the internet, but experience does not go as much as you wanted it to. Like, you can be jumping from, let's say, 50 Mbps connection to 300 Mbps connection. And you're like, huh, it did not become that much better. That's the reason. Is they are limited on that front. Real-time communication needs this. And real-time communication means everything. We need it. The better we get it at this, better stock market handling, better communication, all that jazz does matter. And it's one of those things that you will not see it. It will not be like, oh, we went from 4K to HD, 8K. It won't be something that you can see, but it will be something you will feel. Internet is just snappy. It just works. Things are just efficient. So that would be something that we are looking for, and it will give us very what we call smooth and responsive work, especially for streaming. Like I do live streaming, it could easily have basically more than 10 seconds to 20 seconds of latency. It's like, dude, where are you sending the signal? It's not the signal that is the problem, nor the compute power to crunch that video frame. Is the basically latency that they have to add to make sure that everything remains in sync. Yeah, that's a frustrating part. Again, imagine every big nodes had that atomic system. Now they can have precision time protocol, and it could literally drop down like latency of seconds to sub-a-second. That will be a huge difference. Same goes for basically online gaming. So it's one of those things that I'm truly looking forward to, and I'm happy that even a company like Facebook had the idea of like, hey, what if we open source it? It would be really wise. So this is gonna be a revolutionary thing, but you will not see it, you will feel it. So this was my presentation on basically precision time protocol and the fact that we are having atomic clocks to our PCI Express. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you are free, and as always, thanks for watching.